is a research scientist at Google Research and was previously a PhD student at CMU. He has done a lot of really cool work on understanding generalization, dynamics optimization, dynamics in neural networks, and auto-distribution generalization. And he has this knack of coming up with like really simple examples that break all our intuitions of how we believe theory works. So today he's going to talk about one of those, the pitfalls of next token prediction. Take it away.
Thanks for the kind introduction, Surbi. I hope the mic is working. So yeah, welcome to the talk. I'm really excited to talk about this. This is joint work with my brilliant collaborator, Gregor, who is a PhD student at ETH Zurich. So this talk is about the debate that's on all our minds this morning, a highly confusing and a controversial debate. It's the next token prediction debate, surely. If you have been following AI Twitter, this debate happens quite often. The core of this debate is the fact that people are not sure whether a model that essentially predicts one token after another can really lead us to profound forms of intelligence. Now, I'll describe what the debate is in a few slides from now. But the point I want to make here is that the context in which we wrote this paper was the fact that the arguments in this debate are generally very informal. There are some slightly more formal observations that people have made, and it's scattered across the literature. And we also felt that there are some key points that are missing on both sides of this debate, and we wanted to consolidate this and invite the community to take a closer and a more careful look at this very foundational question. So in part one, I'll discuss what the debate is and what we think is missing on both sides of the arguments. And in part two, I will actually I'll introduce a new failure of next token prediction, which we believe is quite foundational to these models, and we think is more important than many of the problems that we are currently worried about with respect to next token prediction. And in the last part, I'll discuss one possible way to fix this, and this is what I'm most excited about, and I hope I'm able to actually get to the last part of the talk. And feel free to stop me at any point if you have questions. Okay, so okay, what is the debate, and why do I think that both sides are missing something? So usually, this is how the arguments go online. Someone tweets something provocatively, saying something like, "Oh, if humans just said one token after the other without any sort of plan in their mind, and if they're just saying things on the fly, they're just going to meander. They're going to start in one place and then end in another place." Now, usually that tweet will get some 3,000 likes, and then someone will reply or subtweet or quote tweet saying something to the effect of, "Hey, you're trivially incorrect if you paid attention to probability 101. You can take any distribution, whether it's a really dumb distribution or a really intelligent distribution. You can factorize it into these next token probabilities. So it's really not antithetical to intelligence." Now, usually the debate fizzles at this point, but then there's also another point some people make, which is that, sure, yeah, you can factorize it into these next token probabilities, but in practice, there may be small errors, and unless your errors at each step, at each next token probability is 0, you're going to constantly have a probability of seeing errors at each step. So at the end of 200 steps, you would have surely made some error because this is going to exponentially blow up. And to this, one could imagine that an optimist says, "Hey, okay, so you have a really good next token prediction backbone. The problem is that you're just not using it correctly. You're just not eliciting the plan correctly at each stage. The model is able to come up with a really good plan with some small probability of error. And maybe if you could detect these errors, and if you could detect these errors, you could just backtrack and then ask the model to try again. And then maybe with high probability, it would be able to produce a plan from the beginning to the end." So this is usually the template of the arguments that have been floating around. Now, I'm not going to get into the details of each argument here, but my point is the following, which is that, at least for the pessimists here in the audience, there is a gut feeling that next token prediction is not the right bias. It does not somehow, it does not capture the fact that you need to plan your way to a solution. And this sort of an intuition somehow seems really difficult to pin down. And whatever way people seem to be phrasing it seems to be like the optimist can attack those ways in which people phrase this argument. So the point of this talk is to try to find a way to actually pin down this gut feeling that we began writing this paper with. So what is missing on both sides of the debate? So what we observed is that largely all these discussions, like the current discourse, seems to be focusing on the representation problem. Like, can next token prediction represent these distributions that we care about? But what people seem to be missing is this equally, or if not more important question of whether next token predictors can learn these distributions. So what do I mean by that? So there are two kinds of next token prediction. One is what you see in inference, during inference time, which is called autoregression, where you take the output of the model and then you feed it back into the model. But then there's another kind of next token prediction, which is what is often called as teacher forcing, which is what the model experiences during training time, or often during pre-training, where you take a ground truth sentence and you feed it as input, and then you left shift it, and then the model sees that on the output side, and then you back propagate by making sure that the kth target token can witness the ground truth tokens 1 until k minus 1. So even if you sleep for the rest of the talk, I want you to absorb this slide, which is which brings about a distinction between two kinds of next token prediction, which people tend to conflate. Like in all these arguments, people conflate the word next token prediction with autoregression. But I think but what I want to say is that autoregression stands for next token prediction stands for two different things. One is autoregression, the other is teacher forcing. And this distinction is important to make a clear argument pro or against next token prediction. Otherwise, there's going to be a lot of back and forth with people misunderstanding each other. Yeah.
Sorry, just to be sure. So are you saying autoregression corresponds to both of those two things, or depending on the context, one or the other?
Oh, no. So what I'm saying is that autoregression corresponds to only one thing here, which is what you do during inference, where the model consumes its own output. But there is something else that goes on during training, which is often called as teacher forcing. So the umbrella term here is next token prediction, and one incarnation of that is autoregression. The other is teacher forcing. Does that make sense? OK, so the motivating question for the rest of the talk is, sure, yeah, autoregressive models, by which I mean during inference time, the model is next token predicting, can represent any sequence, however complex or however silly the sequence is, any distribution over sequences. But the question that is not clear is whether you can learn any sort of distribution over sequences. So that brings me to the second part of the talk, which is the failure of learning with next token prediction. So the goal for this part of the talk is for me to design a very simple a task that involves planning that is minimal. So by which I mean there will be no language understanding required. So you're not going to see a word problem. And no world knowledge is also required. And I also want the task to be straightforward, which means intuitively, if you as a human took a look at the task, you would know that it's easy to solve. But to make the point even stronger, I will, at some point in the talk, show that this task is actually learnable with gradient descent using architectures we have, just with one small tweak to the objective, but it's not with the next token prediction objective. And given such a minimal and a straightforward task, which I'll show you in the next slide, my point is that training existing architectures with the standard next token prediction objective empirically fails to generalize. And it's not just out of distribution, it also fails to generalize in distribution. Yeah, there's a question.
So, I don't think the hardcore, anybody is like totally hardcore about this. Like, when Ilya says next token prediction, he's saying it's enough to learn about the world. And then, of course, you'll do RL or whatever on top of it. It's never just only.
Okay, at least from my discussions with people, people do tend to say that any distribution should be learnable because okay, they don't use the word learnable. You should be able to capture any distribution using next token prediction. But I agree, like there is a spectrum of points that people are making, and I agree that the most reasonable optimist out there does say what you are trying to say, but I don't think this sort of a failure is known before, and this sort of failure is something they have in their mind. Yeah.
So are you architecture or non-parametric?
Okay, so in this talk, I'm going to focus on the architectures I've talked about here, but I'll also make a conceptual argument, and maybe that should also apply to non-parametric settings, but I don't want to make that claim here. But I'll describe the conceptual argument, and that might convince you one way or the other, hopefully. Was there any other questions? Okay, so this is my claim. So when I show you the task, it's going to look really silly, and it might be tempting to think, oh, this is just a failure on a silly task, but that's the point here. Like the point is to show that there is a simple task where, despite its simplicity, it's going to fail. So it's a negative result. So the task looks something like this. So it's a path star graph. The structure, it has the following structure where there is a central node, and there are 3 legs, okay, multiple legs coming out of it. Here I'm looking at this specific topology, but there are various topologies with different degree and different lengths of these legs. And there is a start node, which is always at the center, and a goal node, which is always at the end of one of the legs. And this is what the task looks like visually, but this is not what I give the model. What we'll give the model is a sequence-to-sequence version of this task, where I take the adjacency list, and I'm going to randomize it. And then I'm also going to tell the model, hey, find a path from the central node 9 to the node 7. And then I'm also going to train the model using next token prediction to predict this ground truth solution, which is 9, 2, 1, and 7. And to be clear, my distribution is going to be over graphs of a fixed topology. So this distribution that I'm trying to visualize here are graphs of degree 3 and path length 4. And each example will look exactly like this, but with the node IDs randomized. So it's not going to be 9, 2, 1, 7 all the time. The node IDs will be randomized. And the way in which I represent it as an adjacency list will also be randomized in each example. So this is the example that I'm going to be discussing. Let me know if you have any clarification questions at this point. OK, if there's no questions. So before we look at what happens when I train a model with next token prediction on this, let's ask ourselves, how would we solve it? So the first obvious solution that people might come up with is to plan, by which I mean you trace out every path that emanates from the center, and then you see where it ends. And then if it doesn't end at the place you want it to end, you backtrack, and then you pick a different path. And you keep doing this until you find the right path. But there's actually a very, very simple solution as well, which is to simply look at the task from a different angle, which is to basically look at the fact that from the goal node, there is exactly one path that's coming back. So it's a unique path, and that's easily recoverable from this adjacency list. So what I do is I look for the goal node, which is 7, and then I look at its uniquely adjacent previous node, 1, and then I look for 1. and then I look for its uniquely adjacent previous node, and so on until I hit 9. So this is a really simple way to solve the problem. And hopefully I've convinced you that intuitively it's easy to solve. And later on, I'll also show you that models can actually learn this problem with a slightly different objective than next token prediction. And therefore, it is actually really an easy problem. Any questions at this point? Yeah.
Does performance change if you ask it to produce the solution from right to left instead?
Yes, yeah, that's exactly what I will show at the end of the talk. Yeah. Okay. So the question is, when I train a model to produce the solution from left to right using next token prediction, will it be able to solve this problem? Empirically, we found that the answer is no. And we also have a conceptual argument for what's going on in this problem. And that's what I'll convince you of in the next few slides. And to do that, let me introduce this terminology of the clever Hans horse. He was a horse from the 1800s or the 1900s who would, the trainer would ask him arithmetic questions, and the horse would respond appropriately. He'll tap, say, 3 times if the question is 2 plus 1, and the audience would be impressed. And then, yeah. Yep.
So do you give the entire context?
Yes. So.
And then you have basically just token by token. So you just, in an autoregressive manner, you create the data set on that.
Exactly. So the question is how exactly do I train the model with next token prediction? This is what I do. So each example is a different graph that looks like this. And yeah, I present the prefix and the ground truth solution to the model on the input side. And on the output side, it's only the left-shifted version of the ground truth solution on which I use the objective. Yeah.
So these are not like pre-trained models in any way, right?
Yeah, we try both from scratch models and one pre-trained model. Yeah. Okay. Okay. Yeah. So coming back to the clever Hans, yeah. So this horse would impress the audience by solving mathematical tasks, and then a couple of decades later, a psychologist came and debunked this by saying that the horse was only cheating by following what the teacher was doing. Basically, the horse would look for some kind of approval or some kind of emotional reaction from the teacher, and it would continue tapping until there was a different reaction, at which point the horse would stop.
The horse was cheating. Just using naturally conditioned reflexes, and then the audience read all that.
Maybe that's how you're going to view the language model as well, because that's my... OK, so my argument here is that something similar happens with the teacher-forced model, that is the model that's trained with next token prediction. This is going to be the densest slide in this talk, so I'll go through this slowly. And I've also just made the problem a little bit more slightly different. I've added some notes just to make it a little bit more interesting. So don't be perplexed by that. Now, OK, so now what do you want your model to do in this task, like during training? So you want the model to learn an end-to-end mapping from the full problem prefix here, which is the adjacency list, and the start and goal state, and find a mapping that goes from there to the full solution, which is the path. So this end-to-end mapping is a complex enough mapping that requires some kind of planning or look ahead, where it has to think of certain things in its head and then emits the answer tokens. But what happens with next token prediction? In next token prediction, you are not going to teach the model this. You're instead going to break the problem down into smaller subproblems, where I not only provide the model with the question, I also provide the model with prefixes of the solution. So these are the like some of the subproblems that the model learns. Now, the first point to observe here is that these subproblems are much easier than the full end-to-end problem. And this comes from the specific structure of the task. We can debate about whether this is true in natural language, like generation tasks. But at least in this sort of a planning task, we see that these smaller subproblems are much easier than the full end-to-end problem. Why? Because all the model needs to do to solve each problem. So for example, here, to predict 13 using this prefix, all the model needs to do is to look for the adjacent token to 11 that's not already up over here. And there's only one adjacent token, which is 13. Is there a question?
You're probably about to say this, but the first step is hard, right?
Yeah, exactly. I'll address that in the next slide. But for now, yeah, what I'm trying to say here is that there are a bunch of subproblems, and all but one of them, I'm yet to address that one subproblem, but nearly all of those problems are really trivial to solve. And this is something we'll see empirically happening as well. Any questions? Yeah.
And your training data. And instead of the label, instead of just being like the correct chain, but you enumerate all the chain and then find out what's the correct one.
I see. Okay, good question. So you're asking, what if I train the model differently by prepending wrong paths and then like basically teaching the model to backtrack in some explicitly. So one way to think of that is teaching the model chain of thought, like you're actually giving chain of thought supervision during training. I think that should help. And we'll discuss that as one potential solution, maybe. Yeah, that should help. But here we are only focusing on the standard next token prediction. Okay. So yeah, so in the previous slide, I showed you that all the subproblems become easy, except for one subproblem, which is the first subproblem. How do you go from node, the start node 9 to the first node 2? Like that's not become any trivial. So maybe the model's still, so yeah, the model may have learned some shortcuts to produce those answers, but then the model still needs to learn how to go from the central node to the first token. Hopefully, like the optimist here might think, hopefully the model can still figure out the actual mapping that's required to go from the full problem to the first token. So once that mapping is learned, then it doesn't matter that it's going to use a shortcuts to produce the rest of the path. So as long as the first node is learned, we should be happy, and maybe that's still possible. But our conceptual argument here is that on the one hand, the previous nodes got really easy to learn. So if you think of these as intermediate supervision, because if you remember in the reversed solution, wherein the model goes from 7 and then figures out that there's a unique path, you can therefore think of those tokens as intermediate supervision, and those are easily lost to this clever Hans cheat. Those are easily learned, so those are no longer part of the supervision. But now the model has to learn the leftover token. Our claim is that, conversely, this token becomes really, really hard to learn. So the first few tokens got really easy to learn, and then now that it's left with this one token as a standalone token to learn, that becomes much, much harder to learn. And intuitively, this is because the model is now posed with a needle in the haystack kind of problem, where it has to figure out on its own which is the right composition of subroutines it has to learn in order to go from 9 to 2. So there are many subroutines here that is involved in this planning task, by which I mean it has to start from 7, then there's a previous token lookup subroutine, and so on, and then it composes those subroutines to get to 2. Now there is no more any supervision to learn those subroutines. The model has to learn that composition without all that supervision. So the problem becomes much harder. And this is something we empirically show. Yeah.
It's hard all along. Why did it be 2? I don't understand.
What do you mean by it's hard all along?
Like It's just some graph connectivity. Like
Yeah.
the first step is just as hard as the third step. I don't understand.
Oh, it's not as okay. So the first, okay. So if the model had to come up with 13.
No, not this specific graph.
Oh no, we are talking about this specific graph topology, like this. Yes. Yeah. Yeah.
So I guess maybe like, okay.
Yeah.
Why is this surprising? So like in some ways, this kind of argument that I guess you sort of said this is not a representational issue. I mean, it's true from universal approximation that you can autoregressively parameterize anything
Yeah.
any order that you like. But like the size of the model in any specific kind of ordering might be much smaller than another one. So like it still could be here that you could sort of reparameterize to go from 7 to 9. That's clearly doesn't require subroutines, doesn't require anything else. So it's like a simpler model. And I guess if we want a more realistic sort of setting, autoregressively left to right is sort of locally okay for text because you can write a sentence left to right. If I force you to write a paper from left to right, it's not going to work very well, right? Like you go back and forth and you sort of like rewrite parts of the paper. So
okay. So later in the talk, I'll show a slightly different objective where the model is still producing the answer from left to right, and it's able to do it successfully in certain settings. So maybe that might answer your question. Yeah.
I wonder, are you going to show that learning the cheating solution does not help learning the first step, or are you going to show learning the cheating solution actually harms learning the first step?
Oh, I see. I'm not going to show that in the talk, but my answer to that would be learning the cheating does not harm the first step, in the sense that some people tend to think that learning the cheating solution overwhelms the model somehow and it's no longer able to learn the first step. But it's more like learning the cheating solution reduces the problem to learning the first step alone. And that standalone problem is really hard to learn from an optimization point of view. Yeah.
I'm a bit puzzled by what you're trying to do, because for me it's kind of obvious that language models have long-term planning. For example, you can ask a language model to write a sonnet. Like, for me, it's one of the most striking things that they can do, because a sonnet has like a very rigid structure. The number of syllables is fixed. Everything has to rhyme. Everything that you choose, I mean, I kind of write a sonnet, it's very difficult. And they choose all those things so that indeed the output is perfect most of the time. So
the point.
Examples where they have this long-term planning, and every thing they choose along the way is a general form. So I wonder if in this particular problem, maybe if experiments you did that was not the case. Maybe it's not something that is very sensitive just to the way you're prompting, or to the way you are eliciting some chain of thought that you could maybe tell the model, these arrows represent a graph, picture the graph and try to find a path, and then tell, and maybe with the solution instructions, then you can do it, so.
Yeah. So okay. So what I understand is that yeah, I agree with you that models can do a lot of amazing things, and I've also you can even ask it to create jokes or write humorous script, and that of course should require a lot of planning. So your question is how would you either reconcile this sort of a finding, or is this finding even relevant for modern models on the tasks that we care about? Yeah, I'll try to address that in the fourth part of the talk. But the long story short is that I think this is still relevant in terms of data efficiency. Are we actually using pre-training data in an efficient, to an optimal manner? So maybe if you throw 3 trillion tokens at the model, some level of planning comes up, but is it the optimal?
100,000 length context. I mean, anything is possible, right?
Sorry.
When the context length by hundreds of thousands. I mean, it's not on the Markov model anymore, right? Almost anything could fit into that.
Not actually.
What?
I mean, even addition is very hard.
Well, but that's, I have a paper where, adding one on binary is hard because it actually requires recursion. And that's very simple. I mean, you just check whether the last bit is 0 or 1. That's a classifier, but it's not built into the task. So yeah, there are issues, but I'm just saying that there's a difference between, let's say, solving an optimal control problem in Markov decision process, which really is quote unquote next token prediction once you fix a policy. But finding a policy requires planning, which requires dynamic programming, and that's a backward induction task. And that seems like to happen at training time. And at test time, you just.
I'll address this in the last part of the talk. Hopefully that clarifies some question. But yeah.
Did you try training it without forward masking? Does it change that?
Without what?
Without forward masking the tokens. Like if you have to do 9, pick 2, but give it 1, 11, and 13, 7.
We do some. That's not what we do. We'll do something like that. I'll get to that in part 3 of the talk. Yeah. Any quick questions? Like I'm running out of time.
Capacity aside, I think Andre mentioned that I keep that for when you talk about it. I think the learning dynamics of the first token prediction might be very, very different from the rest of the task.
Yeah.
So I'm wondering if you have kept training the first token prediction, like you can basically fine-tune the model just on the first token.
Yeah, we tried that too, and it's no different from any.
Quick comment.
Yes, thanks.
It's supposed to be that if your task is sufficiently diverse, maybe things are okay. But if you sort of condition on easy subsets of tasks somehow, like for example, graph connectivity is probably. If you train on general graph connectivity, things are probably okay. But like the specific topology, like if you don't have diversity in your data, the problems arise. Is that just like one takeaway?
I wouldn't say this is so much about diversity, but more about like if there are certain dependencies in the data, like within the context in how you have to implicitly solve. Like if there's a certain chronological dependencies in the text that you see, and I guess, if you don't have data that represents the other chronological, like the reversed version of it, then you would struggle to learn the implicit dependencies. If that makes sense. Okay, because I don't have much time, I'm gonna proceed. But yeah, you can verify the failures that I told you individually, empirically. So for example, I'm just quickly flashing a slide at you. If you teacher force on a wrong node and then ask the model to complete that path, then it continues with the wrong path, indicating that it is executing the clever Hans cheat. And then if you examine the model's accuracy on the first node on unseen test examples, you will see that the model predicts any of the adjacent nodes equally at random, suggesting that it hasn't actually learned how to predict the first node. And putting these together, we can show that it leads to in-distribution failure. So I'll show that in the next slide. So basically, you can take many different graph topologies here and make sure that your training distribution is samples from that topology, and your test distribution also samples from that fixed topology. And then you look at the accuracy. The model ends up achieving trivial accuracy on those unseen examples. So this is in-distribution failure, not out-of-distribution failure. And by trivial accuracy, I mean it achieves 1 over the degree of the graph. Okay, but I have 15 more minutes, so I'm going to rush to what I think is the most interesting part, the part that I'm most excited about, which is, let's try to... Oh, 20. Oh, okay. Okay. So, okay, so we can address a lot more questions later. I'm sorry if I skipped any questions, but hopefully we can revisit them at the appropriate point in the talk. Okay, so I've been talking about next token prediction and the failures of it. Now my proposal here is a slight change to the way we train models, which allows me to learn to predict multiple tokens at once. And we call this teacherless training for a reason, but it's also known as parallel speculative sampling, and that was proposed for efficient decoding. I'll explain what this algorithm is in the slide. Sorry, is there a question? Yeah. Okay. Yeah.
Just let's focus on the first token.
Yeah.
So if we
like a classification.
Yeah.
Now, if you train the model that way, will that make any?
From our experiments, it didn't make any difference. It still struggled to learn the first token. Maybe if you trained for a sufficiently long time and allowed it to grok, it might learn. And we still have that suspicion here. That's what none of this is theoretically proven. But I think what's interesting is the contrast between that sort of a training setup and the training setups that I'm going to show in the next few slides. That brings out a stark difference. But yeah, it's a good thing, a good question to think about. What happens if you just learn the first token? Okay, so yeah, I want to build the talk towards a multi-token prediction technique. Just to refresh our memory, here this is standard next token prediction training. I showed this to you many slides ago. Here, let's say the question is what is 123 plus 123, and the answer is 2, 4, and 6. I'm feeding it on the ground truth answer on the input side, and then I'm left shifting it, and then output k sees the target k sees the ground truth targets 1 until k minus 1. And that's what next token prediction is. But now let's consider a slightly different way of training these models, wherein I just go to the input side and I mask them. By mask, I mean, let's say I replace them with dummy tokens, which are not informative at all. And I don't change anything else. Like I still use the same next token prediction objective, same kind of backpropagation. I change nothing else in the model. So in other words, output k is now looking at the question. It has to, like that's the problem that the model tries to solve, but none of the ground truth answers. So it's just seeing dummy token. So none of the ground truth answer prefix. So in other words, the model is now effectively predicting multiple tokens in advance because all it's doing is looking at this question, and then it's trying to come up with the ground truth targets all at one go without cheating of any sort. Like the teacher isn't revealing any part of the answer to the model during training. And this is also how we do inference. We will do inference for this task, but you can imagine variants of it that please you. But yeah, any questions about the definition of this algorithm or why it is effectively a multi-token prediction technique? Yeah.
This is kind of like reinforcement learning, where the reward comes all at the end of the data instead of throughout the data. Right?
Yeah, that is one nice way to look at it. Yeah. But it's not like reinforcement learning in that the model, you don't sample answers from the model. Like the model doesn't explore the world by producing its own answers and you giving rewards to it.
It's more like the composite action of reinforcement learning, right? Like the point is, in the ordinary method, once you predict 4, you change state. And when you predict 6, you change state again. And in this version, you don't get to change state. You have to do it all at once.
I guess, yeah, that's a good point.
So
yeah, I agree.
Sort of see the result of what you've previously done. And in fact, you have less serialization of the depth of the circuit.
Yeah. Yeah.
The last symbol here is actually less.
Yeah.
You don't see the effect on the world of the
right. Yeah, that's totally correct. Yeah. So what happens if I train the model with this sort of a technique? Okay, so it sometimes solves it and sometimes doesn't, but I think it's interesting because earlier what we saw was that the next token prediction method, the standard training achieved trivial accuracies, meaning 1 over degree. So recall that each bar here corresponds to a different graph topology. And the y-axis is its accuracy on unseen examples from the same topology that it was trained on. And then the other bars here that I'm showing you are the multi-token predictor model that I trained in the previous slide. So what we see is that now the model is actually able to solve for some topologies. It's able to achieve 100% accuracy, which is exciting. But at the same time, there are other topologies where it's failing spectacularly. So it's achieving 0% accuracy. But that's not too worrisome to me because it's not a generalization failure. It's an optimization failure. So in those cases, the model struggles to even achieve perfect training error. So earlier, we had models that memorize the training data set. It memorized the first token in the training data set, to be specific. and then fail to generalize on unseen data points. Here, there seems to be some optimization difficulty, probably for the reasons that that we just discussed. Like the model now has to store its answer internally, or like it no longer can rely on the previous token that it output. So it has to learn a much harder computational graph with fewer resources. But when it does learn it, it learns it successfully. And that's yeah. So this is GPT mini, GPT 2 large. So this is like, I guess, like some 1.5 billion or something. Yeah.
Sorry, like, was it, like, were you able to, like, for the models that were pre-trained, were they, like, fine-tuned?
Yeah, the pre-trained ones were fine-tuned, and the other ones were trained from scratch. Okay. Yeah. Yeah.
So for both the training objective and the inference problem, which, as you've said, are the answer to this might be different for the two of them. Have you tried to identify parameters analytically that would solve the task, so that you know, like, how many, how big a network you would need in order to handle G20,5?
Yeah, that's a good question. I think, yeah, but we haven't. Yeah. We haven't.
Can't do it, like predicting the next symbol of a satisfying assignment.
We'll see. Okay, maybe from the next slide where I show you that the reversed target can be easily learned, one could argue, like one can speculate about that.
The question is whether, like, you have enough juice in the number of layers you have to be able to do the planning.
Well, if you're able to solve the reversed target, all I need to ask the model is to produce the reversed output and then reverse it once more. So the number of layers is sufficient. Maybe the number of autoregressive decodings is what is unclear.
It's not obvious that being able to do it in reverse allows you to do it forward without intermediate steps.
Yeah.
You're using for additional reasoning. So there's a method called quiet star that puts pause tokens in to allow intermediate reasoning.
Yeah.
So that kind of thing might help. Chain of thought helps even more because then every step is able to influence the next step.
Yeah, I agree that it's
and if you're not allowing that, the question is whether you even have the representational capacity to be able to solve it all. If not, maybe that's why you're failing on the larger problem.
I see. That's a good point. I think there is some theoretical work that Matus was also an author on, where they are able to show that something like this can be represented with a log k depth, if k is the path length. So my belief is that it's not a representational issue. It's more of an optimization issue. But yeah, it's speculation at this point. It's what. Yeah.
Quite a bit different.
Okay, I see. Okay.
Change your message and your advanced.
Okay, I see. Thanks. Let's see. Any clarification questions? Okay. I think, okay, this is another interesting observation to some. Maybe it's obvious to some. Basically, you can also train, one thing that's worth trying in this task and is to train the model not to predict the left to right solution, but the right to left solution. So now the model has to first predict 7, and then 1, and then 2, and then 9. And one way to look at this is you're asking the model to progress through the natural ordering of the difficulty of the like. Imagine there's a computational graph, and you're going through the natural order. So it's like a chain of thought. And it's easy because from 7, if you recall, I said that from 7, it's easy to go to 1. It's the one unique node that precedes it, and so on. And if you did this, like, it renders the task trivial. Like, you get 100% accuracy across the board. So, and the reason why this is interesting is that, okay, so what do we know so far? So first, learning to produce the token right to left is trivial in this task. So it is conceptually a really trivial task to solve. And the teacherless training, the multi-token training, is also able to solve it in some occasions and not in some occasions. But the interesting point here that I haven't told you yet is that when it does solve it, it tends to solve it with the similar logic. So even though the teacherless model is presented the targets left to right, it manages to learn it in its own comfortable ordering. So it figures out that the last token is the easiest one to learn, and then it proceeds in the reverse order. And that's what makes it to me, at least, it's disturbing to see that the left to right next token prediction fails. Basically, what this graph tells me is that there is enough supervision in the problem for the model to learn the problem. And there is enough possibility for the model to figure out its own ordering, even though I present a left to right ordering. All I need to do is like make it predict the tokens all at one go rather than one by one. And somehow left to right next token prediction limits the way the model sees the problem, and that constraint creates a lot of obstacles. Yeah.
Next token prediction moving forward. Like if you just randomly mask, it would have been equivalent if you didn't get the wrong reverse order, and then it
yes, yeah, that's true. I have to think about it. It might probably, yeah. If you
next token prediction on the other end of the.
Okay, you're saying it bidirectionally attends, and yeah, that should probably work. Yeah.
So it's not a left to right problem. It's still next token prediction, but it's just.
I wouldn't call that next token prediction though. That's in between token prediction, right? Like you're asking the model to see everything else to the left and right, and then you're asking it to predict something in the middle. That's not next.
You're giving it the positional information. You tell it the position you're predicting is in the middle, but it is next token. It just doesn't know where to append it, right? It just knows to append it in a different place.
Okay, I'm not sure I fully grasped your point. Like, I'd love to settle this, after. Okay. So yeah, this is a specific task. Why should we care about it? Okay, so now I'm going to get into the speculative part of the talk. So the most precise claim that should hopefully offend no one is that this specific task with certain range of graph topologies and learning this with next token prediction with causal masking fails empirically. And this is not due to autoregressive inference or due to the architecture. Hopefully, I've convinced you that the core reason is the way the objective is presented to the model. Now, the slide that is probably going to offend a lot of people, and this is, of course, a highly speculative claim, is that if I took this observation to the extreme, what I'm suggesting is that maybe there is some complex skill out there that is just out of reach for the next token prediction paradigm. Yeah, question.
Really curious. If you trained it, the way that it actually learns it, right? Then cut the model, and now continue to train it using next token prediction. Will it forget? Will it break?
I see.
Next token prediction drive it out.
Yeah, that's a good question. I don't have an answer to it. I guess, it's probably depends on whether you're just fine-tuning the model or you're training it with a large learning rate and things like that. But yeah, it's definitely an interesting question. I haven't tried it.
I don't see, if I can speculate.
Yeah, please go ahead.
I don't see why it should forget. So the problem here is essentially representation learning. And by changing the problem to make it easy to predict 5 steps on as something you're getting immediate reward for, you're learning features that allow you to do that and then work it backwards. So it's kind of like acquiring the representations in right to left order. And once it's got them and they're working, I don't see why you would, training to sharpen the probabilities would move away from those representations. Like once you have them, you should be able to use them.
Yeah, I was asking it sort of, I don't want to take away your time. I was asking it from the perspective of probably if those representations are very sharply learned, right? It'll be hard to move them because they're very good. Right?
Yeah.
That's the problem. I'm wondering along the training path, right? At some point, it's descending on this objective, but the other objective it'll like blow out. That's the question: is when does it? So yeah, that was where I was going.
Okay. Now I actually only have 5 minutes. So okay. I think this is an interesting thought experiment. Regardless of how offensive it is, like I think the thought experiment is if I were to just throw 1 million novels onto these models during pre-training, can it automatically learn the way stories are structured and the nuances in plot twists and plot development. Of course, maybe if I were to prompt the model and or ask it to think step by step, maybe it might accomplish it. But is this something that can just emerge just by training on a bunch of novels with next token prediction? Or to put it a bit more, maybe slightly more agreeable way of phrasing this is maybe the models that we trained with next token prediction to plan to a large extent, like you say, but perhaps there is headroom in being more explicit about teaching it multi-token prediction. And we got lucky with next token prediction that the model is able to plan ahead of time to a certain extent. Maybe there is still headroom. And to make an even more agreeable claim is what I tried to say much earlier in this talk. Maybe there is no skill that's out of reach, and our models can learn anything given 3 trillion tokens. But maybe we are just underutilizing all this data. Maybe if we pre-trained with multi-token prediction, you might see new kinds of things emerging. Who knows? So yeah, actually, I think this is hopefully the most agreeable takeaway that I think more people will, fewer people will find offensive. But yeah, so if you slept through most of my talk, just to remind you, this is my the main point that I want to make, which is, yeah, there's all this debate about next token prediction, and we know that these models can represent anything, and that's trivial. The question that's not clear is whether they can learn any distribution. And I think making this distinction, I think, is important for this debate. And there's many other exciting open questions here about multi-token prediction and whether we can train with chain of thought supervision, or whether we can understand these questions more theoretically and formally. But yeah, that brings me to the end of the talk. I don't know how much time I have now. Okay, but any questions? Yeah.
So first of all, I think this is fantastic work, and extremely interesting. There have been a number of papers that have looked at out of order, so reordering of the variables, like in the sense of the graphical model, as somebody mentioned before, where the tree width is affected. Tree width depends on the ordering. So either at training time or inference time, considering different orders. And I'm thinking of XLNet, NAID, which was neural autoregressive distribution.
Also the Sigma GPT that came recently. Sigma GPT, where they permute.
Right,
yeah.
Sigma GPT.
Yeah.
And then also diffusion models are not autoregressive. And so what's so interesting about your work is you show that eventually you can generate in canonical order. But I wonder if you've been thinking about connection to these other reordering models.
Yeah. Yeah, it's like, for example, in the context of a story, I think it'll be interesting to see if somehow making the model figure out how to produce chapter 11 before chapter 1, so that it knows how to set up the plot twist before it comes to chapter 11 would be interesting. And that's where I found works like the Sigma GPT. He's an next token predictor. But yeah, I guess what I'm most compelled, what I find most compelling with the pass or the teacherless setup is that it requires minimal change. If you're going to propose a completely new architecture, then yeah, I feel like that's harder to challenge the status quo that way. But yeah, it's definitely worth thinking about the relationships between these things. Yeah. Sorry, you raised it. So one. Yeah. Did have. Okay. Yeah.
So maybe it's an optimization problem. It's not the objective.
I would say it's both, because the objective plus the optimization together gave rise to the cheat that the model learned. The cheat that the model learned. Yeah.
I think there was a question about whether there is going to be forgetting, so you can actually check whether the object is smaller for the
Mm-hmm.
the one that you're tracking, and I would imagine that Sybase has optimized the next one.
I see. Yeah, I guess the best way to find out is actually produce something that works with either with the same model and a different objective, or the same objective or a different model, and then see who really is the culprit.
The first token task hasn't changed even when you do teacher test, right? Because
Yeah.
So it's actually something to do with optimization, that you're getting some signals
I
that's
see.
making your representation a little bit better because you're getting sub problems to solve that are not that.
I see. Okay.
So, because the
Okay,
goal
I
is
see.
the same.
I see. Yeah, I agree. Okay. Basically, it took a bad in the standard training, it took a bad trajectory, so it fell into some kind of a local minima, and then
Find that where you get the 3-step, 2-step, 1-step. So you
okay,
the
I see.
representation can get better.
I see. Okay. Yeah, I'm more convinced that it's an optimization issue.
It's like, since we're speculating anyways, like
Yeah.
it feels like somehow this is at least partially advocating somehow some of these kind of category methods like parallel decoding, mass language modeling,
Yep.
because at some point what you're doing in all of them is you're just randomizing the order.
Yeah.
Because data is just too complicated and like it's a mix of tasks. Like maybe
Yeah.
you need to do parsing, some order is like good. Maybe you need to do just like next word prediction and it's a left to right language. So like the previous word is very informative the next time. Like just randomize it.
The real danger is that like all of these examples, there's some word, some observable word, whose prediction is useful. And if you can just find which thing to predict first, you could learn representation. But what if the magic thing you need to predict first is a latent variable? Then you might have more trouble.
Yeah, in that sense, yeah, if you just allow the model to figure it out on its own as to what the first token that it needs to learn is, then yeah, I feel like it seems like that's the best way to go about doing it. But yeah, I'm essentially making an argument for all those kinds of objectives here. Yeah. Oh, we can discuss it offline. Yeah. Yeah.
To the break, to the lunch break, and we thank Vaishnavh again for